Okay, let's talk about 5 Homework 6 and the demo video that goes along with that curriculum within that section. We've been talking about solving simple inequalities and multi-step inequalities. Well, now we're going to talk a little bit about inequalities in two variables. Let me tell you what that means. Inequalities in two variables simply means that you have an inequality, which you can see that we do here, but we have two variables. We have x and we have y. And we're going to be graphing lines in just a second, but first I just kind of want to walk you through some problems, some types of things that you need to know how to do. For example, this part says how to determine if an ordered pair is a solution to this inequality in two variables. So let's just take, for example, an ordered pair. Let's say 0, 0. Easiest ordered pair in the world. Well, if that's a solution, then what I should get when I plug in the x, y values into its appropriate spot, x goes there, y goes there, and when I plug those in, then it should be a true statement. Let's give it a shot. Well, 3 times x, which is 0 in this case, minus 2 times y, which is, 2 times y, which is also 0 in this case, is greater than 12. Let's simplify and see. Well, 3 times 0 is 0, minus 2 times 0 is 0, greater than 12. 0 minus 0, that's 0. Is 0 greater than 12? And the answer is no. That's not a true statement. Therefore, this is not a solution. Let's pick a different ordered pair. Let's say, I don't know, 3, 4. And we could do the same thing. Plug in the x for x and the y for y. 3 times x, which is 3, minus 2 times y, which is 4, greater than 12. So 3 times 3 is 9, minus 2 times 4 is 8, greater than 12. Nine minus 8 is 1, greater than 12. And again, this is not a true statement. Therefore, this is also not a solution. Let's try one more. Let's try the point 1, negative 7. Again, 3 times x, which is 1, minus 2 times y, which is negative 7, greater than 12. 3 times 1 is 3, minus negative 2 times negative 7, or minus 2 times negative 7 is a positive 14, greater than 12. 17, greater than 12. And this is true. So this is a solution. And that's how you determine if an ordered pair is a solution to an inequality in two variables. You're simply plugging in x for x, y for y, and then determining if the inequality at that point, if it is true. If it is true, then it is a solution. Okay, false, if it's a false statement, would be no solution to that inequality. Okay, let's continue. Remember what we talked about when we were graphing our inequalities, when we were just solving our single step or our multiple step inequalities in one variable, that if we have less than, we have an open circle on the graph. If we have greater than, we have an open circle on the graph. But when we include the or equal to, that's when we have to have the filled in circle on the graph. Okay, so I just wanted to kind of draw that to your attention so you remember that, because it's going to be a little different, but I want you to keep that in mind. When we're graphing inequalities in two variables, first of all, we're going to have a line. First of all, if we're graphing inequalities or just dealing with inequalities in two variables, like the one on the previous page was 3x minus 2y is greater than 12. Another example of one might be simply y is greater than or equal to 2x minus 1. What I want you to realize here is this looks an awful lot like y equals 2x minus 1, which would be a line in the form of y equals mx plus b. And that's all we're going to be doing. We're going to be graphing this. It's going to have a line included, and that line will be called a boundary line, and we'll be shading on one side of the line, either the upward portion of the line or below the line. We'll be shading. But we have to know what kind of line, see, because there's different kinds. We can have a solid line. We can also have a dashed line. And here's what makes that solid or dashed. Solid would mean that we have greater than or equal to, less than or equal to. Dashed would mean we have greater than. Sorry, my pen is lagging just a little bit today. Let me try this again. Solid would be either greater than or equal to, less than or equal to. Dashed would be greater than or just less than. So it kind of goes along with, if we have the or equal to's, we have the filled in circles, versus not, we have open circles. So kind of we have these open spots here. So if that kind of helps you out. I just wanted to make sure that you understand that when you graph these inequalities in two variables, you're going to have a line. And that line is a boundary line. And I'll show you, you'll understand more of what I'm talking about boundary line in a second when I graph some of these. But these lines can either be solid or they can be dashed. Again, if they're solid, then the symbol, the inequality symbol, has an or equal to sign in it. If it's dashed, then there will not be an inequality. There's not an or equal to sign. For example, this problem here would have to be a solid line because of the fact that we have an or equal to. Let's take a look. If I just want to graph the line y equals 2x plus 5, I know you know how to do that in your calculator, and you should know how to do that by hand by now. I will review it. This is in the form of y equals mx plus b, where this 5 is my y-intercept, which is right there. It's where it crosses the y-axis. And I have a slope of 2, or 2 over 1, and I can count my slope. I rise 2, 1, 2, run 1, make a point. Rise 2, 1, 2, run 1, make a point. And then I'm just basically connecting my dots. So that line looks like that. Now, if I want to graph the inequality in two variables, notice the only difference is here I have an equal sign, here I have an inequality symbol. Okay? So it's still, notice 2x plus 5, 2x plus 5, it's the same line, so I still start at the 5 on the y-intercept, count my slope, 1, 2, run 1, rise 1, 2, run 1. Before I make my line, I have to see, do I need a dotted or a full line? And because there's an or equals to here, I need the full line. Okay? If this would have just been greater than, without the or equal to here, I would have needed to make this a dashed line. But I'm not finished because, see, this line that I just graphed, this is the line y equals 2x plus 5. But I'm saying this is y is greater than or equal to. That means I have to shade above the line. So I would need to shade this entire portion above the line. Because any point, what this means is that any point or ordered pair that falls above this line, or in this case because it's or equal to or falls on the line, would be a solution to this inequality in two variables. So that's how we shade those. Okay? And that's how that works. We can check this because I can pick an ordered pair. Let's just say I pick, let's say I pick this ordered pair right here. This ordered pair, it looks like this is going to be negative 4, 5. So this ordered pair is negative 4, 5. I can check to see if this is a solution to this just like I did the first thing I showed you how to do in this lesson by plugging in x for x, y for y, and seeing if it's true or false. Let's do that. So here, so I have y is greater than or equal to 2 times x, which in this case is negative 4, plus 5. I guess it would make sense to actually put this instead of y. Notice what I'm going to put here instead of y. I'm going to put 5 because y is 5. See, I substituted negative 4 for x, 5 for y. Now I can simplify. 2 times negative 4 is negative 8. Bring everything else down. Do it one step at a time. Negative 8 plus 5 is negative 3. Now, is 5 greater than or equal to negative 3? Yes. Verifies what I shaded earlier. This is my solution region, and I would shade above the line. Okay? Now, if you have it in the form of y equals, you can always shade above or below depending on if it's y is greater than, excuse me, if it's y is greater than or greater than or equal to, you shade above the line. If it's y is less than or equal to, you shade below the line. Let's continue. Sometimes we're given an inequality in this form, which we should recall that this is in standard form. We learned this when we were writing equations. We have our x's plus our, well, it's almost in standard. If my x's were to the left of y, it would be standard, but it's really close. But it's not in y equals mx plus b where it's easy to graph. So there's a couple of ways we could graph this. One, I could solve for y, and then I could do it the same way I did the other inequality. Or I could graph this using the intercept method. And if you recall the intercept method, what you do is you find the x-intercept and the y-intercept and you plot them, and you just connect the dots. And it's easy to find the intercepts because remember, to find the x-intercept, what we're going to do is we're going to make y equals 0, and we're going to solve for x. Well, this is 0 because anything times 0 is 0, plus 2x less than or equal to 16, which is just 2x less than or equal to 16, divide by 2, and I get the x is less than or equal to 8. What that means is that my x-intercept is positive 8. And unfortunately, it's not really on my graph, so I'll make it on there. It's right there. There's my x-intercept, so I'll make that little dot. Okay? Now to find the y-intercept, I do the opposite. I'm going to have 4x plus, I'm going to make x equals 0, less than or equal to 16, and solve for y. And in this case, I get 4x less than or equal to 16 because this basically goes away at 0. And I get that x is less than or equal to 4. I'm sorry, y. This is a y. Y, I do apologize, but this is a y. There it is. Y is less than or equal to 4, so my y-intercept is 4. Okay? Now, for the purpose of this problem, for the example, I want this to just be less than, because I want to show you how it would look if I did a dotted line. It would have to be just the same line that goes through those 2 points, but it's dashed or dotted. And so now, since my line, the equation is not in the form of y is less than or y is greater than, I can't just shade above or below. I have to find out, well, which side do I shade? And so I need a test point. And the easiest test point in the world is the origin, 0, 0. Because it's simply, you plug in 0 for y, and you plug in 0 for x, less than 16. I think it's so cold that I'm getting a lag in my pen, and I think that might sound funny, but today is the day. I'm recording this on the day we had the big freeze. 16. Okay. Well, we know what this becomes. This all becomes 0 because this is 0 and this is 0. This should be a 2. I don't know why I'm making so many mistakes today. Apologize. But this is 0, less than 16. Is 0 less than 16? Yeah. That means that this is a solution. That means this point is in the solution. That tells me I'm going to be shading below the line. Every point that is in the solution area right there. So I hope you see how that works. It's pretty easy. Just graph the line however you choose to graph, whether it be solving for y and put it in the, just graph by starting with the y-intercept and counting your slope, or finding the intercepts as I did here. Either way, I hope that you find this not to be too difficult and something that you can do pretty easily.